All right. So before opening to questions, I will exercise my right as a moderator to speak endlessly. So, so a couple of things, responses, thoughts triggered by this. First, a very quick thought, quick memory. You showed the hardware, special purpose hardware built, the orrery. Well, Klaus Schulten was my collaborator and Jim's boss as well. He, before coming to Illinois, I don't know exactly how Jim might have some insights, with some of his students had actually built a transputer-based 8-processor computer in his lab, and it still sits there if you go to the Beckman with the signatures of the students. So I think in some sense this renaissance, this wanting to work with computers thing was that he had been doing this for a while. On a different topic, some of you know Uzi Vishkin. He talks about PRAM programming and shared memory stuff and so on, and I disagree with many of the things that he says vehemently, but I'm eternally thankful for him for putting together a workshop in '93 or '94 where he was asking for people to write position papers about, in those days, the HPC challenge, high performance computing challenge program, was in some kind of a jeopardy in those days. Yes.
It was high performance computing and communication.
Right. Okay. And so there was so people had to write position papers, and I wrote a position paper at that time, which allows me now to point and say I told you so that time. Not so much I told you so, but basically I wrote it down at that time what computer scientists should be doing, and part of that, the main point of that was that we need to be designing abstractions based on what the applications actually need. Working with real applications, and that plural is intentional, is the only way to come up with abstractions that last. If you work with one, then you just become a programmer for that, or you develop something that's not enabling enough for the wide field, and if you just develop abstractions without applications, then they are too platonic, just pure beautiful ideas that go nowhere. And so that's one of the main points that I was making there. It's still relevant here. And there was another point that escapes me now, but yeah. So yes, that's the point that Tom reminded me at the end, and I said just now, abstractions. I think the main contribution from computer science that comes is the awareness of good abstractions, software engineering, and Jim pointed to a lot of software engineering kinds of issues, but also abstractions and designing good abstractions, having an eye for good abstractions. And Jeff talked quite a bit about those in his talk earlier. That I think is an excellent way in which we can actually, we need ways in which we can translate the expertise, we can provide the bridge between the disciplines, and abstractions can do that well. So I guess with that I'll turn it over to the audience for questions.
I have to come back here if you want to hold that top of the mic. Okay, but first I didn't know that. While you're finding some of this concept of an eye for good abstractions, I like the way you pose that, because we actually have, we have a hard time understanding which abstractions are good and durable when they only get sort of proven over time. It takes a lot of experience before really good computer scientists recognize, oh, this is the abstraction that's going to fit and really be flexible and last. And that's very hard to do. And a simple example of this is MPI. So all of the vendors, I mean, it was not just a standards process, but all of the vendors had gone through trying to create abstractions that encompass messaging. When you got all those people who had experience and really understood it together, then they could create, the final, the abstractions that they knew really were durable, and they were pretty successful at that. But it's very hard. It really is an eye for abstraction as opposed to.
And I think, like you said, it takes a lot of experience with different things before we can come up with that.
I was going to give another story. About abstractions, right? So I was working with a designer of a certain array-based parallel language, and I was trying to express, well, how do I do this Barnes-Hut algorithm in your array-based parallel language? And the response was, well, this hierarchical mesh, or this Barnes hut tree, is really a hierarchical sparse mesh. And so we should be able to do it. It's like, okay, but that's an abstraction, okay, but it's not the abstraction my brain uses when I'm trying to think of the Barnes hut algorithm. So there's two parts: coming up with abstractions, and then the harder part, coming up with abstractions that really sort of translate into, that we can really think about.
Using your hammer. Shortening an hammer. Yeah. Does that language begin with the A? Begin with the B? No, I think I know the answer. Okay. Other questions, comments from the panels?
I have a comment mainly because I read it's maybe you guys all know it, but I found it recently and discovered that I needed to apply it in my own life. So I'm somewhat of a hypocrite for sharing this. But Steve Jobs has a quote, I guess he put on Twitter at some point, of focus is the ability to ignore a whole bunch of good ideas. I'm paraphrasing, but Apple is the biggest computer company in the world, and they only build a couple types of computers. So on this notion of abstraction, I think one of the things that I really value as an application design person is abstract, but just sufficiently abstract, not too much. There's a lot of abstraction in Apple products, but they don't abstract to the point. I mean, they're fundamentally useful. And I think that's something I'm sure you guys have picked up in 2 decades, is you could go all the way crazy abstract, and then the NAMD guys would just, stick their tongues out and walk away. There would be. It doesn't
happen because we meet every couple of times a week. But
well, yeah.
But you're right.
But
absolutely.
This is, I think,
mechanism
a very important thing, especially in programming models now, is people want to come up with the absolute most beautiful, fantastic programming model that is then, not useful to anyone who thinks about practical stuff.
So one question I had that was triggered, and anyone can answer, but Jim first maybe, is Jim said he used the word trivial the second time, but the first time he said, if things are simple, don't try to make them easier. The thing is that, and recognize that point. In fact, that's my reaction in many cases. Say, well, that's easy enough. Yeah, it might require me a couple more extra lines, but that's not helping me. I can spend that time and it's not helping me improve my program quality. But there is some impact on productivity, and in fact some of this stuff that came up in the charge discussion, where I start to lean the other way, basically saying that, well, if you can reduce the number of errors that you can do, if you can make the code look more readable and more elegant, it is worth something. We need to maybe pay some attention to that. So I wondered if Jim and others want to respond to that.
So part of that, readability and elegance are good, but you have to remember who's going to be reading the code and what their native language is. So, if you can take something that's a loop with 4 different variables in it and 5 lines in C and turn that into a single STL algorithm statement of map this to this, that's great, but a physicist who basically, learns C by sort of, common sense and looking in a book and an analogy can understand what that loop does. And if they need to modify the loop to do something slightly different, they can go in and modify that loop pretty trivially, whereas some of the more, compact but obscure idioms are not the best for highly readable code.
Yep, that's true.
I wanted to, clarify a point. So at one point, Jim said, "Don't build toys," but Pete also told us that we should be building mini apps, or looking at mini apps as a way of communicating. And I think the distinction that we want to think about there is that it goes back to who is the consumer, right? If a computational scientist builds a mini app to be read by computer scientists that actually can work as a medium of exchange, because it's sort of the native language of computer scientists. But if computer scientists build some beautiful new language and throw that out there in the seas of the world as a broadcast to the computational scientists, they're on the wrong wavelength.
So I don't know that Pete said that we should all be doing mini apps. I think you just said that that's the hip thing to do in DOE right now.
I think it's important. I would
No, basically,
Computational scientists can tell computer scientists not to build toys. Computer scientists should tell the computational scientists, please do build toys. That's the
I think absolutely. So there is a producer. I think there's a producer-consumer issue here, right? Which is that computational scientists want technology that is durable and that they can use, that they can trust, as Jim said, and is dependent, and also if the person gets hit by a bus, they can give it to someone else and keep going, right? So they're a consumer in that regard, but they want something that's very durable and useful. Computer scientists, on the other hand, often want something to try out a new idea. And the question is for an application community is, will they have any nervous energy, computer scientists, looking at their problem or not? And what happens probably more often than not is that the application is so big and so complex and can't be run except by a domain expert that a whole bunch of computer scientists who have some interest in that space can't get started because there's no way. And it goes, it's also the point about code, easy to build, configure, make, install, and also documentation, right? So just the things that we expect, the mini apps to have, I think those applications expect the computer science bits to have, which is to be easy to install, be able to get a tutorial and understand it, and so forth. Talking just one comment about the readability of the code. I recently talked to someone who had taught a computer science class, and they told me about one of the assignments they gave, which I just thought was wonderfully evil. And what they do is they assign this very large programming problem at the beginning of the semester. And it's a very large project, many weeks, and the students hand it in, and it's like a 2-semester class. And then near the end of the second semester, they assign a problem that extends something in the code for the first semester problem, without ever warning the students or telling them this, right, along the way. So the assumption is, well, you all saved your code in a repository and you had comments, right? So now go get your code and we're going to extend it in the following ways. And hopefully it's a lesson you learn once and continue with.
So I have this, I don't know, I haven't fully worked it out, but I've tried it a few times, and on the subject of mini apps, I mean, I actually don't really like the idea of mini apps, because I think if you really think hard, I think you can actually come up with a full app that really has all the properties of a mini app if you just are willing to devote the same energy to it and if you focus on readability and distilling down. Turns out most scientific codes are full of crap. I mean, how many lines of NW Chem is actually worth anything? But those lines of code are worth a great deal. And they're actually about the size of the mini apps that I've seen. It's just that it takes a really smart, experienced developer to separate that out. And so the question is, what's the difference between a mini app and a full-scale app where you strip out all the dead code? And so I guess where I'm going with this is there's been a couple of things that I have done where we've basically just done a complete rewrite of something, not trying to come up with a good solution, but all we did is we looked at the existing thing and made a mental specification in our head of what we needed to do, and then we rewrote the thing from scratch. And when we in fact did this to come up with a GPU coupled cluster code, which we had to write in C because Fortran CUDA was not fun, it still isn't, we didn't intend to write the best multi-core CPU code out there. It turns out we did. because in the process of just going through and trying to write a simple, readable, elegant, and not performance idiotic code such that it would map to a GPU, we came up with a code that trivially ran better than all of the codes that are out there that are optimized much more for CPUs. And I look at that and I say, what we need to do is we need to kill all the sacred cows and just force everyone to rewrite their code from scratch every 3 years, because if they do that, you devote the intellectual energy to design rather than maintenance.
I think there is truth to that, but let me say, okay, and then you're going to start distributing your code, and then people are going to say, but I want this bell, and someone is going to say, I want these 2 whistles, and soon it is going to get all the crap that you had in mind, and so that's why you need to rewrite after 3 years.
Open source code is a fishing pole, not a fish.
Right? Any other? Phil?
Just to follow up on that last point about rewriting or redesigning the code every few years and then, feature requests coming in not too long after, I think that that's actually still a possible sustainable solution, because after you do a successive rewrite, you'll see which features people still care about, so you waste no effort maintaining the ones that no one is interested in anymore. And it also means that after the 3rd or 4th time, you'll learn how to architect the code to be able to support those kinds of features that people are interested in, without destroying, everything you've already done. And perhaps you'll actually be able to keep them with lower maintenance. But it requires, this iterative process that eventually teaches whoever is writing these scientific codes, software architecture. And that's a long, drawn-out process, even for good computer scientists.
Well, I mean, my experience is if you actually know what you're doing, it takes 1/10 of the time to rewrite it. I mean, I remember when the first thing I ever wrote that wasn't in MATLAB was when I started working on NW Chem, and I wrote a big fat extension to the TCE for molecular properties. And at the end of it, it was about 6 weeks into my internship, I said, well, this runs, it's correct, but I'm dissatisfied with the abstraction, the design choices I've made, and I literally SVN reverted the whole darn thing. I think I saved a copy in a tarball, but I didn't look at it. I actually then went back and rewrote exactly the same thing, and I was pleasantly surprised that it took me less than 2 weeks, because I already knew what all the right answers were, and I just didn't make any of the stupid mistakes that I did the first time. And I find now that I think if I had to do it again from scratch, I could do it in about a day and a half. So I think these are the things that are underappreciated. Scientists are just fanatically sacred cowish about their code. They think that you cannot possibly throw away your implementation of the Charm 2.1 force field, or, I guess you guys may be familiar with that, but it's not that hard to rewrite stuff from scratch if you have a decent specification and understanding of what's going on.
Which community rewrites their software and turns it over most frequently? Microsoft. I mean, it's a web development. Web development. Yeah, web development. Yeah, that's probably true.
And in fact, in some communities, like in industry, it may not be that they turn over and write their software again and again, just that someone else comes and topples them. So,
well, the web is a good example. If you look at if you did your history of the tool chain in the web space, I mean, it is every year a new piece gets tossed in, and people scrap their old code and rewrite something. There are a couple sustainable pieces in the MySQL sort of back-end piece, but boy, there's a lot of that gets churned. Anybody else? I'm just very curious. I mean, scientists can't be the only curmudgeons here.
No, the problem, I think, is that when you have supported codes that people are using continuously, it is what, was it Rob that talked about in-flight changing stuff. You still are answering your phone and email, and while doing that, it requires kind of at least double staffing, or you need to have some kind of a way of developing the new code while the old one is still being used very extensively.
And also how do you do it, validation and verification if you rewrite your code every 3 years?
Yeah, the web guys have a service model which lets them do that, right?
Yeah.
And the scientific community does not have a service model.
Yeah, so I do accept that what I propose is anathema and NSA. But I actually know people more curmudgeonly even than physicists. People who operate hydroelectric dams, all of their control systems are written in, I think, Pascal or something that came before that. But it's, I mean, something and they basically have to, turn the thing off once all the programmers who know that language die. Actually, funny story about Bank of America is similar type of situation. But yeah, when you do have no room for errors, but I mean, I'm pretty certain that open science physics, I mean, the experimentalists retract a paper a week. So if in the name of good software we screw one, you have to publish an erratum every once in a while, I don't think that's catastrophic.
Audience has been very silent.
Well, one thing I would say, so I can't say I completely subscribe to this, but in one sense, the specification for a piece of software is its source code. I mean, everything that the software does is written down in a formal language that can be mechanically interpreted to carry out that execution.
But you can't tell if it will fall.
Right. Just well, I guess one of the comments can say program should not hold. But, and in science, when you publish a paper, it's the software that was validated. It's not the equations in the paper that were validated. And, sometimes papers go out without certain details of how something works. So getting, a validated specification is, the way you validate a specification is you have someone write up a piece of code that exactly matches that specification, and then you have to validate the piece of code again. So just extracting the specification from existing code would be sort of the first step for what you have to do, is how do we take this? So, what's, I think, more appealing than rewriting from scratch is this evolutionary sense. So this is the intelligent design camp. And if you look at the rest of the planet, every complex system that works has evolved from a simpler complex, a simpler system that works. And,
he writes code in 7 days. He said so.
Yes.
No, 6 days, right?
And take a nap. But so the other question is, or can you take existing code and refactor it to improve the level of abstraction, improve the design without throwing away, whatever knowledge is embedded in that source code?
Yeah, to be fair, I rewrote 20% of one function in NWChem, which I threw away and started over from scratch. I don't actually say NAMD should be thrown away, but I do subscribe to a model where, let's say you've got a guy who wrote a function and then graduated, and he didn't document it correctly. In my opinion, if no one understands what the function does and it can't be engineered out back to a real human-readable specification that isn't C++, the best thing you can do is just rewrite it rather than keep it around. Because I look at code, in various quantum chemistry packages where I don't believe there's a living person who understands what the code means, and saying Fortran with GoTo and Common Blocks is a specification for what that is, I would rather rewrite it from scratch. But it really depends wildly on exactly how bad the problem is. There's some things that can be evolved, and there's some things that need to be destroyed.
There's a sociological aspect. When my very first PhD student graduated, okay, maybe not very first, I was too exact. So when one of my early PhD students graduated, I realized the next student came and said, I can't make sense of the software, I'm going to rewrite. And I realized for a large software base, this is going to be a problem. And then I can't say instituted a really good software practice, but I just became conscious of it and laddered and basically made sure that the next student already knows about the previous software, that I can continue on with that. But maybe I should have taken Jeff's advice and rewritten like 5 times in the middle. Just that I think large functional software, even now in Charm, we sometimes face this problem and say, why not write this whole thing from scratch? And then we think about all our agenda and we say, no, wait, this is not going to happen. We have to do this, this, and this. And so this is actually a challenge. I think there is a lot of merit to rewriting portions from time to time, though. But anyway, I think we are on to a narrow topic. Any other questions from the audience? Yeah.
So I think sometimes it's easier to look at successful collaborations and see what's good about them than it is to sort of sit back and think about in the abstract how computational scientists and computer scientists could work together. So I was just curious if the panel had some thoughts on like who out there, maybe present company excluded, is really doing this well right now and who we should be looking to as examples for how to be successful at this.
That's a really hard question. And once you accept the present company, no.
So one thing that I noticed is that they're often physically co-located. So I don't know if that's the case with the examples you presented, but at Argonne, the cases where it's worked best is where they're down the hall and can share coffee and a blackboard often.
So I'm thinking specifically at Argonne, there's a code GFMC. It's a Green's function Monte Carlo code, and by a physicist who has decorated and gotten many awards. And he works with Rusty Lusk, Ewing Lusk, who has worked on MPI, and they sit and work together, often going to lunch and scribbling down on notepads and using whiteboards. And so that connection that Jim mentioned about the Beckman Institute is I think not doesn't solve the problem, but is a necessary or certainly an important component to that. And the willingness of both to, in some sense, rethink how they're going to solve the problem. When both arrive with that in mind, it has worked very well at Argonne.
In fact, you said often, and that I think is important. My own experience, although Aaron said accepted, but says that actually many of these collaborations, the OpenAtom, Changa, NAMD probably less so, but even there, have required many years to gestate and form the right abstractions, come up with the good design. I think having that luxury of that time to come up with that is useful.
I mean, one of the things that I completely agree with Pete, and I mean, my scientific life changed dramatically once LCF and MCS got stuck in the same building. I won't waste time recounting them, but the joint coffee hour at Argonne, I consider to be one of the most valuable things that we offered, especially to interns, coming to Argonne for the summer. It's an incredibly rich environment to learn crazy stuff. But I will say, though, I mean, we're entering a different world for you. Your world my world, because I'm only 31, but for the next 50 years of scientific collaboration will look different. And we actually, my office mate and I have multiple collaborators in Europe. And I come in first thing in the morning, and he's on Skype with people in Germany with his headphones on. And and then we have Google Chat, and one of the things that I think will be essential for software teams moving forward, especially given some of the constraints of the way the funding is applied, co-location of funding is not rewarded or something like this. That's one of the reasons to pursue some of these, revision control. Distributed version control actually allows people to interact in near real time. You couple that to all the other things. People should really try and get in the mode of trying to create a virtual collaboration environment, because you don't want to restrict yourself just to the people who are within walking distance, although of course that's the best sort of opportunity.
Any other thoughts on Aaron's question from anyone in the audience or panel?
One follow-up to what you said. Recently I heard someone a little more describing it this way, which is that
you need to get people together in a room with a whiteboard for quite a period of time to create the concept for a project. initial gestation and conceptual design is complete, you can have a distributed team. But they saw very few examples of where a distributed team was brought together and then designed something new. And I think that's been at least my experience as well. It's very difficult to do that.
And slightly abstract and not quite exactly realized, but here is an example in OpenAtom, for example. We I idealize it like this, that we, in front of the whiteboard, we design the structure, then we write the parallel structure skeleton of the application using, say, I mean, right now we just do Chum++, but using slightly higher level notation like structure, dagger, or charisma, and then the two can go their separate ways. The parallel skeleton is easy enough to write, and then the parallel guys can try to figure out optimizations, runtime things for that, and the science guys can write their code. At that point, the science that's left is basically the numerical methods. That kind of factoring of expertise might be useful, and the more languages we develop for that, that might facilitate the interaction.
Yeah, I mean, you talk a lot about trust, and I think that, and also not making things too easy. And so this is, I recall Ridgway Scott, who you probably know because he was involved in parallel MD stuff. He was at University of Houston, I think, when Andy McCammon was there, and Cherrick Stratzman was there. And so one of the things that Ridge said about Cherrick was he basically sat in the group and listened to Ridge and his guys talk about algorithms, but they went off after listening very carefully and wrote the whole code himself. And so, and Ridge said he respected that because, you know, it's not only about trusting the other guys, you also have to trust yourself. You have to sort of go back and forth and realize that you've internalized this. One of my projects, they told me what they wanted, they gave me a spec for it, and I gave them a crappy implementation of it in a month rather than a great implementation in 3 months, and then the grad student rewrote the whole thing himself, and it was probably equally crappy, but he fully, we built trust that way, so at the end of it, once I'd written it and he'd written it, we both knew that the other person could write it. And we had a lot, then we were able to be very productive because I was sure that he understood my program. And if I'd given him a high quality version and he'd gone, oh, magic, I couldn't trust him and he couldn't trust himself. So this is a good, I think Jim has the right.
Any other comments? Thank you very much. This was a very useful and interesting discussion from my point of view. And thanks to the audience. And I think we have a coffee break now, right? Yeah. Okay. All right. Thanks.